All right, so we want to continue our examination of this really wonderful paper, The Simple Introduction to Particle Physics. Of course, we're not talking about particle physics, we're talking about general relativity, right? But this, this introduction that they have is very comprehensive, and it includes general relativity. Good luck for us. These guys really put together a nice paper. I haven't read the whole thing, but the part that I really love is this stuff where they interpret curvature, and they have several examples of interpreting the different curvature tensor, the Ricci tensor, which we've done. I didn't do their curvature tensor analysis, but I did their Ricci tensor analysis previously in these lectures. And now I'm really interested in the interpretation of the curvature scalar. And it's funny because the scalar is just a single number, so you'd think its interpretation would be easy. And it is easy to understand, but it's not easy to prove. It's quite a lengthy proof. In fact, here it is. This is the actual paper, right? It sort of begins here with a bunch of definitions, and it immediately goes into this volume element. And we're going to integrate over a volume element on a manifold, so we got to get ready to do that. And then we start preparing. This is just the preparations for the calculations, right? And then it just kind of goes on and keeps going and it keeps going. And right here, this is where they go to use Riemann normal coordinates, right? So right here is exactly why we had to do all of our work on Riemann normal coordinates. So when we did this analysis and we got to this part, we could move through it without waving our hands. Because if you've been following my lectures, I don't like hand waving. I don't like saying, I like making sure we try to go through as much detail as we can that's reasonable. And here it's reasonable. I never discussed normal coordinates. They're an important idea. And here we actually use normal coordinates to make the calculations simpler. And then he goes on, and then they produce all of these little things. They calculate a certain type of metric. They look at that. Look at how beautiful all that is, right? It's really, really wonderful. And then all this stuff kind of collapses down. They introduce a very specific type of coordinate system. Then they keep chugging and chugging and chugging, and finally they execute this integral we were talking about earlier, right down here. This is the integral they were talking about. And then in the end, finally, right there, this is the interpretive equation. That's the equation when a human being can actually look at that, dissemble it, and come up with a picture in their mind that tells them what this number is trying to explain. Right? So that's a long way to go to get there, and I want to go through this whole calculation. But like I said, here's an example of where we were stalled out, or we would have stalled out if you didn't know normal coordinates. So I would get to this point, and then we'd have to lecture all about normal coordinates. So instead, I'm kind of trying to clear this topic first. So I was getting ready to do this, and then I noticed that this thing appears even earlier than the normal coordinates, this idea of the pullback. And that's something I've never talked about. Even in my lectures on what is a manifold, which is really where you would talk about what a pullback and a push forward, that's the dual concept, is called the push forward. That's where you would talk about those things. If you don't understand what a pullback is, this expression, which is a critical expression in this interpretive analysis of theirs, makes no sense. So the purpose of today's lecture is to cover this ground so we can get through this piece of this long analysis. All right, so we're going to talk about the pullback and the push forward, and this is almost like a dual lecture. I should make this supplementary to the What is a Manifold playlist too, because this is about manifolds. Okay, so let's begin. All right, so we're going to begin with a manifold, and that manifold will be called M. And then we're going to introduce a second manifold, which we will call N. So in order to avoid having to say N and M a lot, I'll call this manifold Marshall and this manifold Neal. All right, so and manifold Marshall and manifold Neal. It's extremely important to, whenever I say we're going to start with a manifold, I draw it this way as though it's some kind of sphere or round object or a piece of this plane, but I'm just trying to indicate a set, right? This is supposed to indicate a set. And manifold Marshall, manifold Neal, the one thing that they share for sure, this could be very different objects, but one thing that they're absolutely agreeing on is that they're manifolds. So as soon as you see this, you immediately should think in your mind, okay, the manifold has charts on it, right? And this manifold will have charts on it. And these charts have some degree of overlap, right? And each of these charts has with it a chart map. So if that's the chart U, then say there's a chart map gamma U, which goes into a Euclidean space whose dimensionality equals the dimensionality of the manifold, which I'll call, say, N here. And well, let me see. I'm going to try to be consistent with my notation here. So I'm going to call this V, right? And I'll call this U. And this one, it'll have its, so this will be chart map V. This one will have its map, we'll call it, gamma U, and it goes into its version of Euclidean space, right? That's R, size M, right? And all of these different charts have their own little coordinate system, right? The coordinate system for region U is going to be the coordinates U alpha. The coordinates for region V will be V alpha. So Neil, the manifold, has a chart region V with a coordinate system little v, and manifold Marshall will have chart region U with coordinate system little u, right? This is what you need to think about when you think about a manifold. It has a coordinate system on it. All of this stuff is true, but just because you're thinking of it, that's not, we abbreviate all this, right? It's present in your mind, but that's not how we're going to draw the situation. We're going to draw it in a shorthand form. And that shorthand form could be a lot of different things. I could just say Marshall has a coordinate system U alpha. Neil has a coordinate system, maybe it'll be more of, something like that, and that's V alpha, right? And everything I just said a moment ago applies, but now I'm just drawing the coordinate system right onto the manifold itself, which is a shorthand, right? Because what we're really talking about is there's a region, there's a chart in Marshall and a chart in Neil that has these coordinate systems. So we can talk about the manifold coordinate free, and if we talk about coordinate free, we don't address these charts and coordinate systems. If we say we go to a chart or we go to a coordinate system, we're talking about putting these charts, some real charts on the manifold, and talking about the coordinates of the manifold. Okay, so that's what we think about as soon as we think about manifolds. Now, we're going to introduce something new, right? We've got Marshall and Neil, and I'm going to add a mapping from Marshall to Neil, and I'm going to call that mapping phi. This, I guess in print it would look like that, right? Now phi can be thought of in two ways, the coordinate-free way or the coordinate-based way, and you've got to be able to use both. So if I say there's a point in Marshall, and that point is x, right? I call that point x. How do I look at it? See, I blow it up here. There's x, the point x in Marshall. X is just a element, right? X is an element of the manifold Marshall. It doesn't have coordinates necessarily. If I choose a chart, and I can assign x coordinates, but I may or may not be discussing x in terms of its coordinates. If I'm not, then I just say phi is a function of x, or a function of points on Marshall, and it returns elements in Neil. What element in Neil will it return? Well, there's some, let me clean up Neil's coordinate system here. It will return a point here that we call the image of x, which is a point in Neil, right? So that's the coordinate-free way of looking at it. And now if we actually are interested in these charts, we now say that x has a coordinate. X has a coordinate value in the chart u, right? We're going to name this chart u, and we're going to name this chart v. And so x has a coordinate value in v, and now I can think of phi in terms of coordinates. I can say phi is a function of x0, x1, x2, all the way up to x, I guess would be m minus 1, where little m is the dimensionality of Marshall, right? And it will return, what does it return? Well, it returns the coordinates of this point, of this image point, in nil. But nil is n-dimensional, so there needs to be n of these functions, one to return each coordinate point. So I would call this alpha, right? So there's alpha counts through the dimensions of nil, which if the dimensionality of nil equals little n, and the dimensionality of Marshall equals big M, there's n of these functions, right? And it's the new coordinates over here are functions of the old coordinates. But look how I said that. I said the new coordinates are the functions of the old coordinates. That makes it sound like this is some kind of coordinate transformation. But it's not a coordinate transformation, right? A coordinate transformation, remember how that works. If I'm living inside Marshall and I have another chart, right? And that other chart has its own coordinate system. These charts overlap, and a coordinate transformation takes me from the u coordinates of the chart in Marshall to the red coordinates. I guess this would be call this chart, u2, the u2 coordinates, right? So there's a coordinate system on the chart u and a coordinate system on this red chart. This overlap region, that's where coordinate transformations live. Coordinate transformations live right in here, inside the same manifold. Now, it is true, we're taking a point that has coordinates in u, and we're giving it new coordinates, but we're not just giving it new coordinates inside Marshall. We're actually moving it to a new manifold that has its own coordinate systems, its own charts, and we're picking out one of those charts, and we're giving the old coordinates, new coordinates in a new manifold in a totally different chart structure. So this is not the same. So even though I say the new coordinates in Neal are functions of the old coordinates in Marshall, that does not mean this is a coordinate transformation. This is a function between manifolds. And the dead giveaway is that these manifolds don't have to have the same dimensionality, right? So, if it was a true coordinate transformation, you would be dealing with one manifold, and of course you'd have just as many coordinate transformation functions as you have dimensions in the manifold. Okay, so now, this is the setup for everything we need to know about the two things we want to talk about, which are pullbacks and push forwards. All right, so with this setup, we're going to begin. We're going to move between the coordinate free, but we're going to really lean on the coordinate full definition. Most general relativity is happy to quickly jump into this coordinate picture anyway. Okay, so let's begin. So the whole notion of this topic, pullbacks and push forwards, is all about how this function that goes from Marshall to Neal induces other functions that go from other spaces that necessarily exist because these guys are manifolds. So for example, in Marshall, one of the spaces that exists at every point, including the point x, is the tangent space, right? So the point x will have a tangent space at x, right? It's the tangent space at x in Marshall, right? And Neal, because it's a manifold, will have a tangent space at the image of x, right? It's called the tangent space image of x in Neal. So the question is there some mapping between these two spaces that necessarily exist, is forced upon us because of the existence of this mapping? Right? There's an example of the type of question. And you could ask the same question about the cotangent space, right? If I put a star here, right, and talked about the dual space of Marshall and the dual space of Neal, is there a way of talking about a mapping between those two spaces? I guess this would actually, if it was a dual space, it would look something like this, right? The space of one forms, right? The space of one forms, you would write like this, I think. So the question is given this is the setup, right? This is all we have. We have a manifold, a map between the manifolds. The possibility of a coordinate system is forced upon us because these are manifolds. And we're going to add nothing else to this structure. We're not going to assume connections. We're not going to assume a metric. We're not going to do anything. This is the mathematical universe. And what is forced upon us just by the properties of these things? Well, one thing we know that's forced upon us was the existence of these tangent spaces. And now we're going to ask, are there mappings between these various spaces given this mapping? All right, so that's what we're after. So where do we start? Where do we start with this? And we're going to start with actually something that's particularly easy, right? We're going to consider the space of all functions on Neal. All functions on Neal. Let's say take the points of Neal and return real numbers. I'll draw it this way, right? This is the space of infinitely differentiable functions on Neal. So I take a point from Neal, we get f of, say the point in Neal is y, right? F of y is an element of, say, the real numbers, right? So now I have a function on Neal. That function obviously is not on Marshall, right? The domain of this function is this set, the set of points in Neal. And this is the set of all those functions, right? Picking one function out would be like adding something new to the problem. We're going to pick an arbitrary function on Neal, which means we're kind of dipping into this set of infinitely differentiable functions on Neal. So the question is can we map this set to the set of all infinitely differentiable functions on Marshall, right? Is there a mapping that connects these two sets, right? And the answer is, yeah, there's a pretty obvious mapping that connects these two sets. It's called composition. And composition is pretty obvious, right? Once you realize that this is a function of a point in Neal, well, what you say is, well, I've got this mapping from Marshall to Neal, so presumably if I take a point in Marshall, I can map it to Neal and then apply the function, right? And that is always written simply as f after phi, right? I execute, and then f after phi is a function, right? So this is a function, and its domain is Marshall, right? Remember, x is in Marshall. I guess we should write y is an element of Neal. So now I have a function whose domain is in Marshall, which means it lives in this set, and it only depends on two things. One is some element of the Neal set of continuous functions, and our setup function that connects Marshall to Neal. So this is a real function in here, and we have made a map that goes from the set of infinitely differentiable functions on Neal to the set of infinitely differentiable functions on Marshall. Notice the direction, right? Our function connects Marshall to Neal. It's not necessarily obviously invertible, right? If it was, it could be, or it's not, it could be like a diffeomorphism if it was invertible, but it's not necessarily invertible. We're just talking about functions from Marshall to Neal. But the mapping that's forced upon us goes from Neal to Marshall, or goes from this set associated with Neal to this set associated with Marshall. And this mapping is called the pullback of the function. And I guess the pullback idea is that you're going opposite of the you're going in the opposite direction of our given mapping. You're pulling back from the range space back to the domain space. So this is associated with the range, so you're pulling back into something that's associated with the domain. And this is the pullback function. And so how do we, the notation we would do for this is we would say the pullback is we take the symbol for the original function, put a little star up on top, up above it, and it becomes an operator that acts on functions that live in this space, right? And this is the notation for the pullback of f. I suppose if it's totally unambiguous what this mapping is, you can save a little time and just go with f star, right? But the problem with this notation is it doesn't tell you the name of the mapping that's driving the pullback. As you see, that's absolutely critical. And you also can see that it's hard to imagine going the other way. If you had some function g that lived in this space, that was a function on Marshall, could you somehow use g to get a function on Neal? Well, if you take a point here and you map it to Neal, now you have Neal. You can't apply g to a point in Neal, as g is a function here. But if you take g and you apply it to a function in Marshall, you get a real number, And this mapping doesn't take real numbers to Neal. It takes Marshalls to Neals. So that's not going to work. So there is no way of pushing forward a function from Marshall to Neal, but you can pull back a function from Neal to Marshall, and it's almost trivial, right? It's like, no kidding, right? If I need a point in Neal and I'm sitting in Marshall, well, I just stand somewhere in Marshall, use phi to get into Neal, and then apply the function to wherever I land, right? It's that simple. Another more common way, perhaps, to write this is literally as function composition, f of phi of x. I love talking about notation. Anybody who's been following my lectures knows this. What's the disadvantage of this as opposed to this? Well, this is better, in my opinion, because what ends up on the far right, the arguments clearly identify the domain of this function. So this becomes a function operating on a domain. And that's what we're after. We're after a function on Marshall that operates on Marshall, right? So x is the domain. This is kind of better because it mechanically tells you what's happening. I take a function on Marshall, I apply the function between the two manifolds, and then I apply f, right? Which is what this is saying. This is f after phi, right? And this is still f after phi. This sort of shows you the machine approach. The problem is that the domain of f, this thing, you have to remember that thing lives in Marshall, and this thing is Marshall. So, I'm sorry, this thing here, this outer one, that lives in Neal. This thing here lives in Marshall. So it's kind of, you got to dig through it to figure out what's the domain of things. So at no point in this notation do you have a function whose domain is Marshall and whose range is the real numbers, right? Here, that's exactly what you have. So there's different. So this is the composition, function composition. They're both called function composition, but I prefer the second notation, but I'll probably use both, right? By the way, the notation I'm using for this lecture is the same thing you'll find in Wikipedia on the subject. For example, this is the Wikipedia page about the push forward, right? So I have M and M, and I'm using X and M. Phi is the function. I'll be using X as a sample vector, things like that. I'll try to use this notation down here too. So I've always referred to the Wikipedia page when I get confused about this stuff. So I'm going to try to use that same notation. All right, so this is a summary of what we know so far. There's our pullback. There's our two function spaces. Now we are going to talk about two other necessary spaces. The tangent space at the point X in Marshall, the manifold Marshall, and the tangent space at the point phi of X in Neal. Now we know these two spaces exist. We know tangent spaces exist because we understand that manifolds have tangent spaces at every one of their points. That is just a thing that is a defining feature of what a manifold is. So Marshall and Neal have manifolds at each of their points. And because we have this function, we know that if we have a point X in Marshall, we have a point phi of X in Neal. So this tangent space exists at this point phi of X for sure because of the existence of this function. And likewise, arbitrary points in Marshall by just what they are, they exist, right? So this thing exists and this thing exists. Now what we've found is because this guy exists and because these guys are manifolds and because this existed, we learned that the pullback existed. The question is there an equivalent sort of relationship between the tangent spaces of Marshall at the point X, which is a vector space located at X at the point X, and the tangent space at the point phi of X? Can we connect these two tangent spaces somehow? And just as a reminder, the way we treat tangent spaces is this is the space of all differential operators which form a vector space at X. That's the sort of the coordinate basis. That's how we understand tangent spaces. So each member of this tangent space is really a mapping from C infinity to itself, right? Each member X is a map that takes a function on M to return a function on M. So if I have a vector x in this tangent space, x will act on elements of this set. Likewise, if I picked a vector, say y, from this tangent space, that would be a map from this space to from the continuous functions on Neal back to itself. So we can actually broker the existence of the pullback, which necessarily exists, to create a mapping between these two spaces. And you can almost, it's sort of it's a little more subtle than the pullback itself, but there's really only one way to do it, so it's not that subtle. And the way it's going to work is if I take a vector from the tangent space of x and I operate on the pullback of a function, so I take that vector and I operate on the pullback of a function on Neal, I should get the same thing as there should be some vector in the tangent space at phi of x of Neal that gives me the same result. And that is going to be called the push forward. And the push forward is symbolized by phi at x of push forward acting on the vector x. And this guy is an element of this tangent space, so it acts on just the function x, f. Right? So you can almost put brackets around it, right? Because this is an element of this tangent space, so it acts on this function. So that's the way we define a map from a vector x, which is an element of this tangent space, to a vector in the tangent space located at phi of x. So I will write this down and just discuss it a little bit more detail here. First, let me erase this and notice, first of all, the direction. The direction goes from Marshall's tangent space to Neal's tangent space. So it follows the same direction as the transfer function. I'm trying to call this the transfer function, the connecting Marshall to Neal, just to give it a name. So it follows the direction of the transfer function, and the definition would be the vector x acting on the pullback of a function on Neal equals the push forward of x acting on the function of Neal, right? And this is a little bit odd in one sense, because the right-hand side of that expression seems to be a function on Neal, and the left-hand side is a function on Marshall, right? In other words, f is a member of this set, and the pullback of f is a member of this set. And so the pullback of f, its domain is points in Marshall, but f, its domain is the points of Neal. So it seems like you've got different domains here, right? Because this here is a member of this set. So this guy is a map from this set to itself. We talked about that a moment ago, right? And so this side is a member of that set, and this side is a member of that set. And it seems like setting them equal is a little bit of an awkward thing to do. And the way I keep track of this in my mind is I understand that f is always going to take a point in Neal, and f after phi is always going to take a point in Marshall. So the way to think about this, I would offer to keep it clear in your mind, is if you write it this way. That is, include this guy evaluated at x and this guy evaluated at phi of x, and understand that x can be any point in Marshall. X can be any point in Marshall. Oh, wait a minute. Did I get that backwards? Hold on. Yeah, of course. This is backwards, right? This needs to be f is a function on Neil, so its domain is, this one's 5x, and this one is x, right? So I evaluate the pullback function at some point x, and here we evaluate the, we evaluate the pullback function at x, and then we evaluate this expression on that function evaluated at x. This will be a number, and then here you evaluate, you take the push forward, operate on f, and evaluate the whole thing at 5x. In fact, that's probably the proper way to do it, is to put brackets around this, right? Like that. See, so what you're doing is you're evaluating this whole thing, which is a function here, and then you evaluate that function at 5x, and here you evaluate this whole thing, which is a function in this, and you evaluate that guy at arbitrary x. And this should be true for all the x's and 5x's. So this is how you define the push forward. And the notation here, we can quickly go back to the Wikipedia stuff. Let me do that for a moment just to show you where I derive this notation. Well, first let me just say there's a variety of notations for this, for the push forward of a vector. One notation is what I've written here, phi at x, right, star, right, that's the push forward, where the star is supposed to be sort of dual to this star up here, where the pullback star is up and the push forward star is down. So I can do that operating on a vector x, which is a member of the tangent space at x. That's why you need to keep that little x there. But you also see d of phi x operating on x. And you also see, I think the most common one is little d phi of x acting on x, right? You have all these different choices. And if you go back to the Wikipedia page, you can see here, for example, right, the differentials expressed in these terms. I don't see that very often. That's terribly confusing. But notice you always have to keep track of what point you're dealing with, which tells you what tangent space you're actually creating the differential for. So that's very important. You've got to track that. But it can be any tangent space. And likewise, you usually have to indicate the transfer function that's involved, because this all depends on the transfer function. And then you have these assorted choices of notation. And here you see this version of the definition, right? The way we would have done it is we just previously went phi x star instead of that, but you don't obviously have to do it that way. This is a very standard way of doing it. Oh, and over here, instead of using the pullback notation, phi star of f, they just use the literal definition of it, f after phi, and that's all fine. So the point being that this pullback and push forward stuff and these differentials have tons of notational things, and every book will be different, and the age of the book matters a lot. Which choice you use, the style of the writing matters, and the exact field. If you're reading about general relativity will generally use this notation. If you're doing something purely mathematical and abstract, you'll probably see this notation. You know what? It looks like I reversed it. This notation goes phi star x, and I think if you look at the way I did it back here, I went phi x star. I don't know why I did that. I think phi star x actually does make a little more sense. So I should probably interchange star and x right there. It's not a huge deal, but the idea is to keep track of your sense of what notation you choose to use. Before I go on, let me point out, we've done this all in the abstract, right? Notice none of this leans on coordinates, right? These functions are functions of points in Neil. These are vectors in a vector space without an identifiable basis, right? So all this is coordinate free right now. At the end of the lecture, we're going to throw down coordinates and show how these things would actually be calculated if we were given a coordinate system. In fact, just to make that clear, let me erase this part right here so we don't think that there's some sort of coordinates. Now, I do have chart maps U and V, so we're kind of set up for that. So I should really, notice we haven't referred to them anywhere in this process yet, right? This is completely coordinate free. Coordinate free right now. Okay, so when I finished this lecture completely, I had actually done an entire section on the next pullback, which is from form fields, right? Fields of, I guess, one forms on Neil, pulling back to fields of one form on Marshall. Now, notice these are fields, right? This was a push forward of a vector in a single tangent space at a point forward. But here we pull back an entire field. And there's a reason for that. But the lecture started getting very long. In fact, I think it was an hour and 10 minutes. So I'm splitting it in 2 lectures. So this lecture covered pullbacks of functions and push forwards of vectors. And now the next lecture is going to be about pullbacks of form fields. And then we're going to also talk about the pullback of tensor fields. And then we are actually going to use the coordinates, right? Then we're going to cast everything in terms of coordinates, which is a very practical way of calculating what these pull forward or pullbacks and push forwards actually are. Okay, so next time we'll finish up with our pullbacks of covector fields, and then we'll and that those pullbacks, just like we brokered the pullback of functions to create the push forwards of vectors, we're going to broker the push forward of vectors to define the pullback of these covector fields. But anyway, we'll do that next time. So I'm splitting these up into 2 lectures that are more like 40 minutes instead of one long one.